Okay, I hope all of you are back. So the next contribution is by Salman Koley. He will talk about the seismic measurements that were done in the last year. Salman, please go ahead.
Can you hear me?
Yes.
So hello everyone. So today I'll be talking about the seismic studies that we conducted at Terzitt in Limburg. So I'll go straight away to the next slide. So I'll discuss today. First, we'll give an overview of the entire presentation, and then we will first discuss the surface measurements. So the arrays that were deployed on the surface and what we got from them. Then we will discuss a bit about the borehole studies. Then we will discuss again another surface measurement, which is the active seismic survey that was conducted. And then we will go on to the underground seismic noise characteristics. And to end with, we will discuss the Newtonian noise estimations that we have done so far. So basically the geology at Limburg, as we all know by now, is characterized by a few layers of soft soil over a hard rock. And that transition occurs approximately at around 30 to 45, 50 meters. So that depends a bit from point to point. So here, the main idea that we always want to take away is that, so you see here's a simulation of the ground motion that we would observe. So you see that if there's a source on the surface, most of the noise is basically trapped in the first few layers of the soft soil. And then by the time it reaches beyond the hard rock, it's almost gone. It reduces by over like 4 orders of magnitude in power. So, and then we did lots of studies, including borehole studies and everything. So we will discuss everything in this talk. And of course, this type of attenuation is very important for us because we have many cities nearby. So even like these cities are basically not transient sources, they're very stationary sources. So even during the night, they will be active at low frequencies. So it's important to attenuate those noise sources, and this geology would help us. That's the idea. Going to the next slide. So we started conducting the seismic studies around 2017. So the first studies were done using 2 arrays of seismometers. A total of 74 seismometers were used. We carried out measurements for a period of about 3 weeks. We had 2 rings of seismometers, so which you see here as array B and array A. And on the right, you have the power spectral density plots of basically acceleration square per hertz. So here you see the Peterson low noise and the high noise models, and then you see the curves in black, green, blue, and red as the measure on the surface. And the magenta curve is the one that was measured at the Hymansgrove during the same period. So this is for one particular day. So you see, if you even go 10 meters deep, because the Hymansgrove is at the bedrock, it already attenuates the seismic noise by over an order of magnitude, or even actually more. So this is the first measurement that we did. So what did we get from it? So from any passive seismic measurement, we measure the ambient noise. And then from the ambient noise, we try to infer that from what direction the noise is coming and with what velocities the noise is propagating. Now the velocities will depend on the mode of propagation of the wave, basically. So whether it's a dominantly surface wave or body wave. So what we found out from the results was that the dominant mode of propagation that we observed was from rally waves, because we dominantly did vertical, we only did vertical measurements. The sensors are only vertical component. So we will talk only about rally waves. So we observed the fundamental mode to be dominant till around 5 hertz, and above 5 hertz, we had both the fundamental and the first overtone. So here you see in these plots, these are basically typical outputs from beamforming. So on the radial axis, you have the slowness, and the azimuth is measured clockwise from the north. So for example, in these figures, you see that there is a source that is originating south of the array, basically. So there's a road there. Important things to observe in this is that this blob of energy, this goes far away from the center as you go to high frequencies. That would mean that the velocities are basically decreasing or the slowness is increasing. And typical things to observe are here. You see the 2 rings here. So that would mean that one is the fundamental and one is the first overtone. We verified it because it is the first overtone and not a body wave. We don't know it because we knew of the geological region. So we expected where to really expect the overtone. So from that, we can confidently say that it's the first overtone. Going to the next slide. So from this beamforming outputs, you can easily decipher the phase velocity of the surface wave, which is rally wave in this case. So for the first array, which was the bigger array, we observed the first overtone and the fundamental. So the rally wave velocities here show a sharp drop from about 1000 meters per second to 400 meters per second between 2.5 and 4 hertz. So which implies that there is something going on in that, because there's a sharp drop. So that would mean that there is from a transition from hard rock to soft soil. So to talk about the observations, higher modes were not observed by the smaller array. So that could be due to 2 reasons. That is the depth to hard rock in that beneath that particular array slightly increases. And it could also be that the array was actually too close to the source that was generating this noise. So if the array is too close, then you don't have higher order modes. You don't observe higher order modes. So now you want, in order to use this phase velocity curve to get a velocity model, subsurface velocity model, we need to have some borehole information, some constants to model. So we did several borehole loggings in the first borehole that we had in 2017. So that includes like gamma ray, single conductivity measurements. So the gamma ray is again divided into a spectral gamma ray. So you have the potassium, the uranium, the thorium content of the soil. So this basically gives you which soil, how clayey a soil is basically. So more potassium, the more the clay. So from these measurements, you can basically break down the geology of the region into up to maybe say 140 meters into a 5-layer model already. And the transition from soft soil to hard rock, that's this part, it occurs at around 35 meters for that particular borehole. It might change slightly by 10, 15 meters, but that's it. So now we have this information. We know how many layers to go for, what are the expected velocities in those layers from sonic logging. So we use them. And then what we do is we do an inversion to get the subsurface velocity model beneath each of the arrays. So array A and array B separately. So why we did 2 arrays? Because we knew that there was a fault, there was an overthrust fault running between these 2 arrays. So we divided into 2 arrays. So the first array, you see that there is a transition from soft soil. So these are the S-wave velocities. So you see a transition from soft soil to hard rock around 35 to 40 meters. But beneath array B, which is the smaller one, you see that the transition occurs around at 50 meters. So that is what I said earlier, that there is a fault. So the bedrock is higher beneath array A and is much lower beneath array B. So the rock goes down beneath array B. And also the contrast in the velocities that you observe from soft soil to hard rock is slightly lower for array B. Now, from these passive measurements, what happens is that you only get the information about the S-wave velocities, because the P-wave velocities are not so trustworthy that you get because they have low sensitivity. So that is why we did active seismic campaign. So here in this figure, it's the same spot again, basically where the 2 rings were. So here with the star, you see the borehole that we have there right now. This red and the green lines show you the source lines. So the sources were distributed along these lines, and the receivers are this blue and the magenta one. So the receivers were spaced at around 3 meters, and the sources were spaced at twice that, 6 meters. So that was just to get a good foldage of the data. The figure on the right, that gives you in Cartesian coordinates like how much the length were. So the length of each of the receiver lines were approximately, I think, around 450 to 500 meters, I would say. And the maximum source receiver offset was around 953 meters in one case, in one line, and 776 meters in the other line. So why this is important? Because then you would know that up to what maximum depth you can go when you do imaging. So it's around quarter of that. So let's say 200 meters or so. So now we wanted to do seismic reflection processing, but from the data we got was because of the soft soil or hard rock thing, there were lots of guided waves and the reflections were kind of obscured by them. So what we went for was seismic refraction tomography. So what you do in seismic refraction tomography is you have a source, you have the receivers, you get the first arrival times, you pick them, and then you use those first arrival times to image the subsurface. Now, these first arrival times are composed of 2 things. One is the direct waves, and another is the refraction. So after certain offset, the refraction gets faster than the direct arrival because it follows Snell's law basically in a layered media. So here we have the 2 smooth P-wave velocity models that we got underneath each of the receiver lines. So here, as I stated earlier, so you see that the depth to bedrock actually increases when you go more towards a smaller array, and the depth to bedrock is slightly less towards the larger array. And here there is overthrust fault, and the dotted lines basically show you the strike of the fault. So sorry, the dip of the fault. So the velocities are around of the order, let's say, on the top, it starts between 800 to 1,000 meters per second. And then by the time you get to the hard rock, it's around 2,500 to 3,000 meters per second. And it can go as high as 4 kilometers per second at a 200 meters deep or so. And the models here we got are up to, I think, accurate up to 200 meters deep. As I said, the quarter wavelength thing. So next, so the surface thing is done. Now let's go to the underground seismic noise. So what we have here is we have a seismometer on the surface now, just above the borehole, and then we have a seismometer underground. So the underground seismometer is a STS5 seismometer, and the one on top is a Trillium T240. So on the first figure, I show you the H/V ratio, spectral ratio that we observe on the surface. So here you see that there is a peak at around 4 hertz, and the peak value is quite high actually. It's a value of 7, which if you consider global standards, it's quite high. And that is typically because there is a transition from soft soil to hard rock. So there is a resonance, and then that resonance builds up the energy of the horizontal spectrogram as compared to the vertical. So because there's there's a PSV conversion. So this value is high. And on the figure in the bottom, you have the power spectral density plots on the surface. So the magenta one is on the surface, and the blue one is at the bottom. Interesting thing is, of course, I'll talk about the attenuation later. But of course, I see a few peaks there, of course, which we don't know yet why these peaks are, but these are very sharp spectral peaks, and they occur at 2.1, 2.3, 3.1, 6.3, 6.7 hertz or so. And we show these measurements for both horizontal and vertical component. Next, let's talk about the microseismic variation that we have at the site. So, I mean, lots of studies have been done previously, and globally it is observed that during the summer, the microseismic peak due to the ocean interaction with the coast is higher during summer and less during winter. So that is what we typically observe at the site. So here on the figures, you have the power spectral density, which we averaged between 0.1 and 0.5 hertz. So we are talking about the secondary microseism. So the black line is basically the average during the summer, and the blue one is during winter. So there is a drop of about an order of magnitude in the microseism compared between summer and winter. Next one. So that was the low frequency part. Now going on to the part we are more interested in, that's beyond 2 hertz. So what we did was we did similar averaging of the power spectral density between 2 and 10 hertz. So the figure on the left here, it shows you the variation as a function of days. For example, a few days in November. So you see that there's a typical diurnal variation here, high during the night and low during the high during day and low during the night. And this reduction is of the order about let's say 2 orders of magnitude in power. But while you go underground, which is the red curve, this reduction goes about a factor of 3 to 4 in power. So something is happening. So we will explain what is happening later on. And here, the figure on the right, here you see the same, basically the red curve, but the red curve is zoomed. And then an interesting feature in this is that during the weekend, the seismic noise underground actually goes even further down by a factor 2 as compared to during weekdays. Now, this attenuation, now what we can do is that we can compare the power spectral density observed on the surface and the underground. And the figure on the left shows you the attenuation in the horizontal component, basically. So up to 4 hertz, I think they're both. So we compare the attenuation both during night and day. So they are together almost up to 4 hertz. Above 4 hertz, the attenuation during attenuation during day actually is higher, and the attenuation during night is slightly lower. So why is that? It's because that this frequency band of the ambient seismic noise is not dominated by surface waves. So it's more importantly dominated by body waves maybe. So that's why up to 4 hertz it's almost the same, but after 4 hertz it's slightly different. And overall, if you see, we get a reduction of magnet power of the order 10 to the power 4. Yeah, they're comparable during day and night. Next, what we hypothesize that since the attenuation during the night and the days are different, so why that is happening? Okay, of course, one reason could be that the sources are very far away during the night. So that's why you get a less attenuation. So another idea what we picked up on was that there could be a body wave background. So body wave background, I don't mean body wave sources, but the background body wave that is present all the time. So we wanted to compute that. So what happens is you first know that during the day, what is the attenuation level? So given the sources were there during the night, you know what you would expect underground, but you don't observe that underground. You observe slightly higher. So that difference actually contributes to the body wave background. So here you see that the blue curves are basically, blue and the red curves are basically the body wave backgrounds that you computed. And the black curves in both these cases are basically the spectra that we observe underground. So the thing we learn from this is that the contribution of the body wave background to the measurements that we do underground is almost more than 50%. So there could be, I mean, maybe if you go a few hundred meters deep, it would not benefit you much because the contribution of the body wave background would anyway be there. Next, towards modeling neutrino noise. Now, since we have these velocity models and these dispersion curves that we got previously, the Rayleigh wave dispersion curves, and we have the source distribution. So what we do is we use this geological model, a layered model, along with the source distribution, and then we model that using an illustrodynamic solver. So here, for example, you see that we solve the entire wave equation, which comprises of P waves, S waves, love waves, and Rayleigh waves. And it also includes mode conversions, so like the PSV conversions. So once you know the ground motion, the idea is to simulate the ground motion everywhere surrounding a test mass. So we use the solver to get the ground motion everywhere, depending on the geological information and the source distribution information. So from that, you have basically, here I show you a plot of how the energy varies as a function of depth. So here I had a ring of sources, and then the ring of sources becomes lighter and lighter and lighter as you go at around 250 meters deep. And here on the green and the magenta are the observed spectra on the surface and the underground, and the black ones are that we try to reproduce. Now, with this model, we have a slight error around 4 Hertz because that is where the H/V ratio also peaks. So that is one thing to be figured out. We are not very confident about that part of the region. And then from using this, we computed the Newtonian noise using the simulated ground motion. And here on the curve in the green, I show you the mean, and then the band, of course, shows you the 10 to the 19 percentiles. So we are again not sure about this particular region around 4 Hertz, but the other part is quite reliable. Although I would still say it's preliminary. Now, the things that I would like to do in future is, or things that might have increased the error in our case, is that we don't have 3-component measurements on the surface. So then you don't know what the force mechanism is. So that is one thing I would like to know that will improve our results. Then, of course, we want to match the observed H/V ratio around 4 Hertz even underground, which we don't do it now because there's some problem with how you place the sources and what is the mechanism. Another thing that we would also do is consider the contribution of background body waves, because that has not been taken into account while computing the Newtonian noise in this case. Of course, that is very marginal, but still we need to include that. And as I said previously, it would be very nice to have a string of geophones down a borehole to constrain the surface of eigenfunctions, because now it's only simulation. There's only one at the top, one at the bottom. So nothing, we don't know anything about in between, any observations. So that would be very good. Yeah, that's it. Thank you. Questions, please.
Okay, thank you, Shalman. I see there is a hand raised by Peter.
Yes, I'm Peter Van. Shalman, what do you mean on attenuation?
It's the attenuation in power between the surface and the underground.
Simply divided the noise level. So what?
Yes. Simply divide the observed spectral density on the surface, and yeah.
The mean, you mean, and divide the mean noise? No.
So what we do is we always do it in percentiles. So, for example, if I have one year of data, I take 10-minute segments, and then with 50% overlap between segments. So every segment I divide, and then I have a distribution basically. So okay, then the bands, what you see here, so the bands basically are the 10th and 98th percentiles, and the blue one is basically the mean. Yeah.
Okay, thank you.
Alexander?
Yes, thank you. I have a few questions. First of all, thank you very much for a very nice presentation. I think my main question is that I understand all your modeling for the noise propagation. You did all the simulation from the noise sources placed at the surface. Have you ever considered that some of the energy and propagate in the subsurface to the Einstein instrument level from some sources in underground activity? And second question, if you allow me, for your seismic Rayleigh wave inversion, you show the curves of inversion, but what is the reliable depth of your inversion? In other words, what are uncertainties in your inversion? Thank you.
Okay, so to answer your first question, so when you do measurements with your with surface arrays, the surface arrays are insensitive to depth. So you only know the distribution of sources on the surface. So if I had to do a simulation with sources underground, that would be of course possible. But then there is, I mean, I could put a windmill somewhere, but I don't have any like relevant proof of any underground source. So one thing that we always talk about is the body wave background. So the background is of course built from sources that are underground, maybe far away or even close. So yeah, that is possible. But from my surface array studies, I don't have any evidence of including our underground source. But yeah, sure, we can include it. To answer your second question, the uncertainty. So I give you the depth models, I think up to 80 meters or so. So how I would put it is, so it's slightly complicated if you have to study the sensitivity curves. But overall, the idea is our lowest frequency of interest that we studied was 2.6 Hertz. So the velocity is around 2.6 Hertz, it's 1200 meters per second. So if you divide 1200 by 2.6, that is around how much? 10 by 4. So that is around, let's say, 200 to 300 meters. And the sensitivity is up to a lambda by 3. So that would be around 100 meters. So we are sensitive up to 100 meters from ambient seismic studies. Of course, if you study lower frequencies, your depth of investigation increases. But for that, you need larger arrays. So our array in this case was, for example, maximum aperture of 500 meters. So yeah, if you want to do that, you can do that. But for us, it was like 100 meters.
Yeah, just, okay. So what is the lowest frequency from the surface waves you measure?
2.6 Hertz.
2.6, yeah, thank you.
And also on the underground sources, Schaumann was showing some spikes in the PSDs at certain frequencies. And one of the suspicions that we have is that there's lignite mining many kilometers away, and we might see signals from that.
Yeah, yeah, sure. Yeah.
Yes, I would like to add to that. So from my experience at Virgo, so we have the windmill noise there. So that is peaked at 1.67 hertz. So that is also a very sharp peak there. So these peaks also look very similar, but I cannot say that if it's a windmill or anything. But of course, I think it's a source at depth, because the attenuation, because if you see the attenuation, that there is a slight drop in attenuation actually at these peaks also. So this at the lower attenuation actually means that these are not surface waves, but these are body waves. So now they could be on the surface, on the underground, that I don't know. But yeah, actually, I think Frank can tell you, like, we are also trying to do surveys in the future.
Marco?
Yes, please, can you hear me? Okay. Well, my question is, you mentioned that there are no human seismic sources around, but from the map, I can see a railway at about 2 kilometers, and there is Aachen that is 250,000 people in 10 kilometers. These would create disturbance in the frequency band, I would suspect. Okay,
so I never said that there are no human sources. Of course, there are human sources. Like the borehole that you have a house there, you have a camping ground there. People are walking all the time there. People are driving. So yeah, of course there are sources. But the point is that you have a good geology there also. So you see that the day-night variation on the surface is about 2 orders of magnitude, and the day-night variation at the borehole is about a factor of 3 to 4. So if all the surface waves on the surface would go underground, you would still observe the same amount of attenuation, like same amount of variation. But you don't. Of course, some part of the surface wave leaks to the bore to 250 meters deep, but it's only below, I think, 2 to 3 hertz. Above that, I think most of it is attenuated. Of course, because of the wavelength. The wavelength of surface waves at high frequencies are much higher, so they don't go underground.
Enrico, do you have a short question?
Yes, thank you. Now, my short question is, when we look at the surface waves, the coupling, the Newtonian noise coupling is not just to the fact that they produce seismic noise at minus 205 meters or so, but through the direct gravitational coupling is not taken into account.
No, that is taken into account in the integral.
Can you talk louder? Like, I can't hear properly actually.
No, but it is taken into account. Okay.
So what we do is we do a full wave solution. So that has body waves and surface waves.
No, but also in the Newtonian noise integral, you integrate up to the surface. So what's
exactly. Yeah.
Alessandro, do you still have your hand raised? Do you still have a question, or is that left over?
No, I think it's left over, but I still have a question. If you have a few moments, I can ask a question.
I prefer
if not, okay, then please just carry on.
Okay, then thanks, Schaumann. I think we should carry on. Please stop sharing the screen.
Sorry, there are a few questions. There are a few questions on the chat, so maybe Suman can reply there directly.
Oh yeah, Schaumann, look at the chat window and give answers in the chat window, please. Okay, we continue with another talk on infrastructure, and that is by Florian Amann. Please, Florian.
Thank you. Yo, can you hear me and see my screen?
Yes.
Yeah. Okay. I would like to give you a little bit of insight today on the site selection procedure. I cannot tell you anything about that. Sorry, my telephone is ringing all the time, and some geotechnical challenges which drive our strategy for the current site investigation program. I know you have seen this and it becomes boring, this figure here, but the noise is a very important problem, and this is also what makes it different to a normal and standard tunnel planning, because we have, despite the geology and geotechnical question, fault zones and karstified areas, we have also to consider in the selection procedure the noise and the noise damping characteristics of the ground. And how we do this currently in our site selection procedure, despite, as I said, other important factors, we look at buffer zones around infrastructure, which is which we know is emanating noise. It's streets, roads, wind power plants, and what you see here on the figure is this is, for example, wind farms. They have different sites, and we just put a buffer zone around it. And here you see the roads, and here you see railways. And we would like to stay away from these sources of noise. At the moment, the buffer zones here are from literature, or they are estimated, and we have to bring on both feet on the ground on this, and we have to know how this changes. It depends on the wind direction and the wind speed and the size of the windmill. And what we are having in mind at the moment is a systematic noise measurement on the surface and also on the subsurface, using additional boreholes and surface array. And we have to somehow confirm or adjust these buffer zones for a more detailed planning. How it looks like at the moment, here you see the same map, and here you see some possibilities how to place an Einstein telescope. And here you see the boreholes we have planning at the moment in the next 14 months. This maybe is the first borehole starting early 2021. And then we have additional boreholes. In total, we plan 5 boreholes with a 250 meter depth, which are used for geotechnical characterization and geological modeling, of course, but later on we want to make them absolutely dry and deploy some seismometers in there. This is what we are planning now. In December, we start with this. Here you see the wind park of Aachen. Here you see the Tierzit borehole where Suman was talking about. Here's a permanent station. And we deploy a couple of arrays in the field here at different locations over the Christmas time, mostly to see how the noise is changing as we go away from these windmills. There's some challenges, as I said, which drive our site investigation program, and I borrowed here some very nice drawings from NICEF. You see these big caverns here. Here as a scale, you see a person. This is the drawing as it looks like at NICEF, and when we turn it into an engineering design, it looks more boring. But we see what is required. Here are caverns which are 30 meter high with some span up to 25 meters. And this is in general a little bit of a challenge here. I show you some figure. This is in Iceland and this is in Austria. Here as a scale, you see the truck down here. This is something we cannot excavate from the floor of a tunnel, so we have to build additional tunnels like this here to access the crown. Here you see access to the crown, and then you would dig the tunnel downwards in these areas. So of course we have to place this cavern outside environmental noise buffer zones. What I also have to mention here, this is a size of caverns we are not usually using in standard civil tunneling. You would see such big caverns as the example shown here in hydropower plants or in mines. And there you have flexibility, how you would like to orient your axis in respect to the geological structures. So you can optimize your orientation, and this is not or only reduced possible for the Einstein telescope because we have to build a triangle and we cannot turn the cavern axis as we want. So what we have to find here in our site investigation program is a stable, massive ground. We would like to stay away from fault zones, heavily fractured zones. And of course, we also consider the orientation of the caverns in respect to geological structures. Another challenge might be associated with the tunneling. It's a lot of questions about how we excavate with a drill and blast or with a TBM makes a difference in the excavation radius. It's only 1 meter here, as you see, between drill and blast and TBM, but we talk about 30 kilometers of tunnel, and there's a lot of excavation material which has to be dumped somewhere in an environmental friendly way. And then there's another question of the accuracy of the tunnel lining. The requirements, as we understand, for the Einstein telescope are much larger than for conventional tunneling. So we were looking into also solutions for this. This is gyroscope controlled TBM excavation, for example, to get really this absolute straight tunnel from one corner point to the other. Problematic zones, this is what we don't want to have here, right? Could be a problem. So we have tried to identify, but we have not identified yet any of problematic zone which can lead to something you see in the figure here. But also high permeability is a problem. I have shown a graph here. This is a tail race tunnel in crystalline rock, much stiffer than about the same overburden. And you see here the line of sight displacement from satellite radar images. And you see here up to 5 centimeters of deformation on the surface. And this is at the locations where the water inflow to the tunnel was highest. So what you get is a poroelastic response and consolidation. And you see it up to the surface. 5 centimeters is not very much, only if there's very, very sensitive infrastructure on the ground. But this is something we have to investigate in great detail because we have to expect there will be a steady state inflow into the tunnel as we operate the Einstein telescope. You may argue, oh, why you don't build it fully watertight? This is a good point, but usually because of static reasons, I would say below 100 and 200 or 200 meter, when you build an impervious lining without drainage, is technically extremely challenging. So you have to heavily reinforce, and it's extremely cost intensive. What we have to consider or anticipate here is an impervious tunnel lining, of course, but we have to drain the water, and so we have a steady state ongoing water inflow. So we work very detailed on detailed hydrogeological investigation to not end up with the situation I show here in the photos. We have to know how much we can do with grouting, so we can grout the rock mass to reduce the inflow. Then maybe we have to think about tilting the entire telescope so the water can run off in certain directions. And we need to have dewatering facilities. And as you see here on the sketch, my mouse is not working very well. It's long 900 meter long dewatering tunnels and dewatering shafts. The reason for that is you need pumps, and pumps emanate noise. And so we would like to see them far away from the corner point. Another challenge here is the access tunnel. You see that soft rock over hard rock is very nice for the noise, but challenging for tunneling because we have to go through the soft rock. And this all in a topography which I would consider flat. I know people in Netherlands and Belgium are very proud about their hills, but I would say it's absolutely flat with a slight roughness. So this brings me to the point that we have to go from the surface underground. So we have to do something which we not really like in tunneling. We have to go downwards, and downwards means I have to be very careful about the hydrogeological situation, about permeability, and there's different options we can do this. It could be an inclined shaft, a helical shaft, a ramp, which I would like to avoid because of the soft rock conditions here. This would be a possibility, or a shaft. So what we have to do is we have to start on the surface and go, like you see here on the right hand side, with a conventional shaft sinking, which is quite a job to do, right? But it's possible. But you have to avoid that. These people here working on the floor of the shaft, they don't get wet. So we have to make sure that it is geologically absolutely tight as much as we can get here, or you have to grout it systematically to keep your construction site watertight. So this is what we are doing, is we integrate at the moment all data which are available in the region in a GIS project. So what you can see here, and this was quite some work to do to harmonize the geological surface information from the 3 countries. This is another example. What we collect is all boreholes which have been drilled not by us, which have been drilled in the past, which are deeper than 20 meters. So they give us a lot of information, and all this goes finally with information on all the details of these fault zones and so on in a 3-dimensional geological model of the entire region. What we also do and started before we start drilling is we investigated outcrops of all the different formation we expect at the level of the Einstein telescope, and also at the level of the access tunnels. You see here a map of outcrops which we were looking at. We did laser scanning, photogrammetric studies. We drilled boreholes into this to get first information about strengths and fracturing, rock mass characteristics. You see here how this looked like. So this has been done already systematically in the entire area as a basis to see what is the variability of the rock mass we have to anticipate it at depth, and how what can we learn from this in terms of tunnel design, excavation methods, and so on. There's 5 new boreholes planned, as I showed already in my slide before. 5 boreholes of 250 meter depth. They serve as geological exploration boreholes, but also are important information for the geological modeling, which is currently ongoing. We plan an excessive geomechanical testing program. As an example here, the strength of the rock mass maybe does matter more in the weaker rock up there, and the stronger rocks down there. They're really strong for the shallow tunnel. It's still only 250 meters. But we also have to investigate the properties which are relevant to estimate the performance and the penetration of mechanical excavation. So all this is currently underway. Then we have, as I said already, hydraulics play a major role. We have a intensive hydraulic testing, in situ testing program in all 5 boreholes using PACA systems of different interval lengths, using pumped and unpumped fiber optics to see the inflows, and many other tests are planned and currently out. The tender is out for that. Then we have planned stress measurements, also hydraulic fracturing or hydraulic testing of pre-existing fractures to get stress information, stress orientation of the region, and an intensive program of geophysical borehole logging. What you see here is an acoustic televiewer, here a televiewer. So we get an unwrapped image of the borehole wall, which allows us to fit sinusoidal curves through the structure, and we get structural information, and so the geometry. We will also see if there is any karstified zones. We have the karst more into the southeast of the perimeter, but this is something we would like to avoid. It's maybe polyocast. It's not as bad as active cast, but it is not something we would like to have. And especially we also want to see fault zones within our boreholes for the hydraulics and also for the geotechnical characterization. And then once we have finished these boreholes, we plan a lining in the boreholes, which allows us to operate seismometers in an absolute dry borehole over a long period of time. I was quickly really fast, but my last slide for today. We also plan an intensive seismic, active seismic survey. We cannot tell you at the moment the exact route, but we go over the perimeter in 2 times in north-south direction and 3 times in east-west direction. We try to use, of course, existing infrastructure to not disturb the people so much, but also this is in a tender at the moment, and we have to confirm all the different places where, or the line where we want to go for the seismic survey. This is already my last slide, and I just want to mention here again the funding organization for e-tests and all the partners involved in e-tests. And thank you very much for your attention. I didn't follow the chat now. Oh, there's 28 questions. Maybe not for me.
No, thanks, Florian. No, there are many discussions going on the chat window. Thanks. Are there any questions for Florian? Michele, you have your hand up?
Yes. So, I mean, looking to the slide number 4, I'm puzzled by the distribution of the triangle of AT. None of them has a vertex in Germany.
Yeah.
Why? Is it just, I mean, you are not testing anything in Germany?
Yeah, it's a political thing. We had this discussion already a couple of times, and it seems that the political situation in Germany, they don't insist on having such a corner point in Germany. We even heard that people warn that building such a telescope over 3 countries with all the different regulations could be a nightmare. And currently, with the noise situation in the region, we have no corner point in Germany.
Okay, this has some impact on the available funding because if we intend to use regional funds, okay, it's I mean, it has not a negligible impact.
As far as I understand, it should not but this is something which is discussed all the time now.
Okay.
I have a question. Yesterday there was a presentation by John Osborne about the situation at CERN, also for the FCC, and he was stating that to study the site, we should spend something like up to 3% of the total construction budget right now for studies. Do you feel comfortable with the way we are doing things right now?
Yeah, I feel very comfortable. The number 2 to 3% is a good number. I always like to show the uncertainties of cost estimations versus actual costs. And as when you come in the range of 2 to 3% of the total investment with your site investigation program, then your estimates are having the lowest uncertainties for the costs. With 5 boreholes, we cannot survive, of course. It is feasibility study, and once we have identified corner points and the maybe problematic zones, we have to do more. Absolutely.
Are there more questions on the chat window? No, I don't think so. Okay, Florian, thanks again.
Thank you.
Then we should continue. So the next talk is by Takushiushiushiyama. It's on the experience at Kagura. Of course, Kagura is already like a pathfinder for ET in some sense. So I think there's a lot that we can learn.
Yeah.
Can you share the screen?
Yeah. Can you my slide?
Yes.
Yes.
Yeah, it's good to see.
Okay. Yeah, thank you very much. Thank you for inviting Kagura for this ET meeting. So today I'd like to talk about site and infrastructure of Kagura. So here shows the topics I prepared for today. So this page shows the old figure which presented a future gravitational wave detector plan presented in a news magazine of our institute in 1993. So I surprised with this plan had already included use of an underground site like this. So anyway, you may know we constructed Kagura in the Kamioka mine underground site. So Kamioka is 30 kilometers from Tokyo, and a good point of Kamioka is Kamioka mine is made of old and hard rock of gneiss. And another good point is scientific facilities such as the Super Kamiokande neutrino detector existed. They helped and supported us a lot. On the other hand, a bad point of Kamioka site is Kamioka is with heavy snow in winter season. As a result, enormous amount of spring water after the snow season. It is a quite serious issue for Kagura. So this slide here shows general information of Kagura. You may know Kagura is a laser interferometric gravitational wave detector with 3 kilometer arm length, and many collaborators has joined. And the project started from 2010. And here shows information about tunnel excavation. Excavation took about two years, and total length we excavated about 8,000 meters. And the method, excavation method we used was NATOM, New Australian Tunneling Method. Here shows a history of Kagura, but I skipped it today. So this is a Kagura tunnel, and here is a corner station, and this is a X-arm and X-end station, and this is a Y-arm and Y-end station. Y-arm is rotated by 28 degrees from the north, and sea level at the corner station is about 3,070 meters. And one of the unique features of Kagura tunnel is a two-layer structure for each station to utilize hard rocks as a suspension stable basis. Can you see these vertical holes? So here shows a schematic view of test mass suspension system. Here is a ground level, and here is the basis of suspension point, and here is the second floor. Here shows a standard cross section of arm tunnels, width of 4 meters and height of 4 meters. This is a standard tunnels. Arm tunnels has a slope of 1/300 in order to drain the water to rivers naturally. On the other hand, for each station, it has a horizontal planes prepared for easiness during installation of vacuum chambers or so. In the case of Kagura, highest X-end is the highest place and Y-end is the lowest place. I like to move to the next topics, seismic motion. So small seismic motion is an important reason of constructing Kagura in the underground site. So that we investigated before how much Kagura should be made inside in order to obtain small seismic motion as we expected. So in order to investigate, we measured seismic motion at several places along the existing tunnels, this line. And we used this accelerometer, which is interferometer type. Here shows measurement results of seismic motion at the outside. So this is this graph shows a seismic motion frequency, and seismic motion is a unit of meter per root hertz. And the blue line shows city area, seismic motion measured at the city area. On the other hand, this black line shows the seismic motion measured at the center of Kamioka mine here. And the red and green line shows seismic motion measured at the outside. Green line shows measured at this point, and the red line shows measured at this point. So, so this figure shows even in Kamioka, where is far from city area. So even in Kamioka, seismic motion at the outside is the same level, above 10 hertz in city area. This is one result. And here shows measurement results of seismic motion in the tunnels. So this figure shows seismic motion in the unit of meter per root hertz, frequency from 1 hertz. This black dashed line shows seismic motion measured at the outside here. And red, blue, and green shows seismic motion measured in the tunnels. So blue line shows 50 meters from the mine entrance. Green line shows 100 meters, and blue red line shows 800 meters inside. According to this result, small seismic motion is available inside 50 meters or more. So that we constructed all the experimental rooms of Kagura inside 200 meters or more. you may be interested in real seismic motion in Kagura site. So here shows a seismic motion of Kagura in the unit of velocity. This graph shows a displacement of seismic motion of Kagura. Both measurements are the same place in second floor in Xn. And this plot made by 1 year measurement results. So I should say two things. So here, in the Kagura site, 10 to minus 9 meter per root hertz level is realized. So it is a good point. On the other hand, microseismic motion around 0.3 hertz is terrible. So, and it is very serious for interferometer controls for Kaguras. And it is excited by intense ocean waves due to bad weather. Next topic is
We lost your voice. I don't know if you're talking, but we don't hear you. At least I don't hear you.
Me too.
Me neither.
Can you put something in the chat window so that we know that we still have a connection?
And the slides froze.
Okay, so let's give it a few seconds. Okay, he made it until slide 14. Then maybe it makes sense to then continue with the next talk, because we have no idea when he will come back. And then if Takashi comes back, we can finish with him. Okay, any other suggestions? Good, then let's do that. And the only question is, can I stop sharing the screen? Because I don't know how we can do that. Atwish, can you do this?
Yes. I'm trying to do it, but it doesn't seem to work.
Luigi, have you sent a message to Takashi?
Yeah, I did it already in the chat window, but
No, but not the chat. So in the ordinary mail.
Okay, I managed to stop the sharing if you want to go on.
okay, I emailed him. Nevertheless, I think we should continue. Paulo, can you take over?
Yeah, no problem.
Okay, very good.
So, hope you see the screen.
Yes, we see content, yes.
Okay. So thank you very much for giving me the chance to present CERN vacuum technology for the Einstein telescope. And I talk on behalf of my group, Vacuum Surfaces and Coating Group. So, okay. So this is the content of this brief talk. First of all, I go through the CERN planning, a brief overview of what are the vacuum system at CERN. I introduce also my group with a brief introduction, and then I will go for a selected number of facilities and competencies that we have at CERN. I will give you an example of ongoing activities, and if you are interested about our activities that we perform, you have additional slides in the presentation. So LHC is our biggest accelerator and is the last step of a chain of acceleration, a chain of accelerator. And this is the timeline. We are today in the long shutdown 2. Part of the injector are already, as you see in yellow there, are already in commissioning phase after the long shutdown, while the LHC is for the moment still in the cooling phase of the cryomagnets. The beam is expected in the LHC for February 2022, and then we are going to have 3 years of intense running. And finally, in 2025, we will start what is called the long shutdown 3, which is the final implementation of the high luminosity LHC. So what is the high luminosity LHC? It is the most important at the present CERN project. It has an objective to increase the integrated luminosity, so the number of collisions up to 250 inverse femtobarn. The two detector with the highest luminosity, Atlas and CMS, and these are for the following 12 years. Of course, vacuum systems have the objective to guarantee the performance and the gas density required for the beams at the different stages of the acceleration chain of the LHC. At the very beginning, when we have just the production of proton and the first ring of acceleration, we don't have a stringent requirement of vacuum. We go from 210 to -7 in the LINAC, where we pump essentially with, at the beginning, particularly in the RFQ, by turbomolecular pump. And then we go to 10 to the -8 in the proton synchrotron, where we pump with ion pumps and in particular in the PS with titanium sublimators. In the other part of the LHC, where we need a much lower vacuum, much higher vacuum, sorry, lower pressure, we have two strategies for pumping. The one for the room temperature areas, where we massively pump with non-evaporable jet thin films. We have a 6 kilometer coated with 1 micrometer of this film, titanium, zirconium, and vanadium. While in the cryogenic parts, of course, we profit from a fantastic cryogenic system, which give us surfaces at 1.9 Kelvin, which is the temperature of the cold mass of the magnets. We have in total 127 kilometers of beam pipe, I'm sorry, of a vacuum system, and 50 of them are cryogenic, are insulation vacuum for the transport of cryogenic fluids. The availability of our system are, from my point of view, quite exceptional. So to run all these, we have a group dedicated to that. It is a multi-purpose and multidisciplinary group, which is called Vacuum Surfaces and Coating. I have the pleasure to lead this group, and the structure of this group is essentially designed with respect to the competencies from operation to mechanical engineering and design, interlock control and monitoring, and surface chemistry and coating, and finally a small unit to tackle the problems of the next, the future project and the present studies. We have also a certain number of students, PhD, master students, and postdoc, which help us essentially for projects and studies. So this group has as a main objective the operation and the maintenance and the consolidation of vacuum systems, but we are deeply involved in high luminosity LHC, of which we have one work packages, which is the packages of the vacuum. And also we help intensively the high energy physics community, providing them with services like, in particular, surface treatments and analysis. And then we have important participation in the future studies, accelerator future studies, and collaboration. We have some collaboration. We hope that the gravitational wave community, we provide to the community of the gravitational wave a substantial collaboration in the next years. I'm showing here a selected number of facilities that we have that might be interesting also for your community and the associated competencies. So I start with the building 107, which is a recently inaugurated building for surface treatment, chemical surface treatments. We have also inside a printed circuit board, but this is led by another group. And this building, we cover practically all chemical surface treatment that are used for accelerator and large scientific instruments. Here you have two pictures there, and in the second picture on your right, at the end there you see where the people are there, the long bath where we do cleaning for UHV purposes. This year, so we have this bath for the cleaning, which is the simplest, but the most required, and also the essential step for any additional surface treatment. We have the possibility to clean vacuum components as long as 7.5 meter and 1 meter diameter by immersion. If we have biggest components, we have to work with circulation of fluids. And here you see the drying furnace. A typical example of production that we had in the last months, I would say, is one that is quite famous at Nikef, is the thinning with caustic soda down to 150 micrometer of the vertex locator of LHCb RF box window. Is a very, very delicate work that was performed, I think, successfully by Nikef and our laboratories. Then in the second picture, in the center, you see a niobium, a bulk niobium cavity, which is called crab cavity. During the cleaning, there we can clean the surface, polish the surface of niobium, and at the same time, we have the possibility of rotation on different axes. And this is this rotation is possible even if inside there we have acid like hydrofluoric acid. In the last picture, you see on your right, you see the facility we have for the electroplating of different metals. Copper, silver, rhodium, palladium, nickel, and gold are the most demanded. So here you see a typical example of a treatment that we do for external institute. This is the DRF tank of the LINAC for the European Spallation Source in Lund, Sweden. where we are in charge of the copper plating in the inner surface, as you see there. And the dimension is, I think, is around 80 centimeter diameter. So another pole of expertise in the group is coatings, thin film coatings. And our experience focuses essentially in one main activity, which is coating in situ, so inside the accelerators. As you see here in your right, we are preparing for coating inside a cryomagnet. This is a prototype of an amorphous carbon film to reduce multipacting phenomena. And the magnet is 5 centimeter in diameter, they call the bore, and 16 meter long. Another important activity is coating in vacuum chambers, big vacuum chamber with a high aspect ratio, with a length of a maximum 8 meter, because this was required by accelerators, but in theory there is no limitation for that. In addition to long vacuum chambers, we coat also on samples on different materials. For example, we can coat mirrors, glass, polymers, and for example, ceramics. We can coat with a very, very thin layer of titanium ceramics to avoid charge built up on the surface of this material. Another important line of coating activity is the, as I already mentioned, is the non-evaporable jet coating. Is a titanium, zirconium, vanadium alloy deposited on the surface of beam pipes. And for that, we coated 1,200 vacuum chambers for the LHC, and continuously we continue to coat because we have a change in the layout, so we have to provide the coating for that. Of course, once you clean and you coat the surfaces, you have to characterize the surfaces. So you have to accept in terms of vacuum requirement by vacuum measurements. And here in these two pictures, you see our building 113, where we have 1,000 square meter with tens of a vacuum system, where we can measure the property of all vacuum chambers, all material and shape useful for our accelerator and also accelerator in the community. A typical example is this vacuum chamber, which is neck coated, and the central part is made of beryllium for the point of collision of the accelerators. We also, just a second. We also provide quantitative measurements. This is one of the most important points of our characterization. And this is because we have calibrated the vacuum instruments, in particular residual gas analyzer and ionization gauges. Surface analysis is also another important pole of expertise, because with these techniques we can measure the functional properties of materials, in particular secondary electron yield and change of composition when bombarding with electrons and a cyclotron light. Chemical analysis is also important. We provide this kind of measurement for CERN community. And the most important technique that we use for vacuum application is the Fourier transform infrared spectroscopy, with which we characterize contaminations, hydrocarbon contamination on surfaces. And I know that these techniques was already used in the gravitational wave community, in particular for LIGO, to detect any contamination on the surfaces of the vacuum pipes. Leak detection is another important pole of expertise, in particular for cryogenic systems and for system of difficult access, where we developed very special tools to detect and give a quantitative value of the leak detection. And here I show an example, which is the ARIA experiments. Is a distillation tower to purify argon installed in Sardinia, in a mine in Sardinia. And for that, we gave the support, CERN gave the support for the leak detection. I give you here finally an example which can be interesting for you. Other examples are in the slides if you want to have a look at the presentation. This concerns the outgassing rate measurement of what is called mild steel or low carbon steel, which is an interesting material for the vacuum chambers of the vacuum tanks of gravitational wave detectors, and because of its cost. Is extremely cheap with respect to austenitic stainless steel. For example, the 304L, which is, I think, used for the American and the European facilities. So for that, we started just a few months ago, and we bought some selected steels that have good properties for welding, weldability, and also for other purpose. And a limited cost. And we started by using small samples. You see these yellow, is a hot sample during heating. The first measurement is the temperature program desorption, in which the sample is heated progressively and uniformly to high temperature. And we measure by a quantitative gas analysis the gas coming out from the sample. So what we have shown is that is quite striking, I would say, is that there is an important difference between the austenitic stainless steel and the mild steel in terms of gas release. In particular for hydrogen, you see that the blue curve on the top there is the desorption of hydrogen as a function of temperature for the 304. While all the curves down there, except the orange one, which is the background of the system, are those for the mild steel. Which this reflects on the fact that the total content of hydrogen for the mild steel is roughly, two order of magnitude lower than the one for austenitic steel. Then after that, we measured the outgassing rate of samples and vacuum chambers. And for that, we have 3 different ways to measure it. And I present here only the most sensitive. In this system, we have a measuring system, a measuring vacuum system with gauges and quadruple mass spectrometer. And this brown chamber here is where we have the installed samples, or the chamber itself can be the sample. So we process the vacuum system as usual with the bakeout. We apply the bakeout that we want to the chamber or the sample. And then when everything is a good temperature, we close this valve here, just close to the brown sample. We close it and we let the gas accumulate, the released gas accumulate into the chamber itself, the brown one. Then after a certain time, we gently open this variable leak valve and we detect the gas coming out from this accumulation volume, which can be also the chamber itself. We integrated it and we of course divide by the time and the surface, and we can obtain what is called the specific outgassing rate. This is a picture of the system. Here in front you see the spectrometer and the pumping units, and the vacuum chamber is in the left side of the picture. So the results, in the results we compare austenitic stainless steel 304L as received, I repeat, as received, and mild steel as received. These samples underwent a cycle, thermal cycle of 24 hours at 150 degrees, and this accumulation done at room temperature lasted 24 hours. What you see is really impressive, is that the peak, the blue peak related to the mild steel is extremely small, okay, and mostly related to the movement of the valve. And while the peak of the austenitic stainless steel is very large and with a long tail. So integrating all that, it gives an autogassing rate for the mild steel which is lower than 310 to minus 14 millibar liter second square centimeter, which is at least 2 orders of magnitude lower than the one of the as received 304L. Unfortunately, there's always some drawbacks because it will be too beautiful. The situation. Certainly there's something which is wrong as is usual, and this is the case for the water pumping. In fact, this material is, as you know very well, is prone to heavily oxidize, and we expect for that a rougher surface than the one for austenitic stainless steel. And when you pump down without any bakeout, in effect, the water vapor autogassing rate is 10 times higher than the one used as a standard for austenitic stainless steel. This difference is probably due to the surface roughness or the chemical composition, and this is the subject on which we are focusing our attention in these days. And this is done by different techniques, in particular surface analysis, to understand what is going there. Then concluding remarks, I think I gave you the evidence that CERN has competencies and facilities in vacuum technology that could be useful for the Einstein telescope. So sharing our experience will be certainly profitable for the ET at different level, from R&D to installation and operation details. But on the other hand, this collaboration would be extremely beneficial for CERN because we can anticipate subjects that will be extremely important for the future of the present accelerator and maybe also for future accelerator, like cost reduction, innovative and fast pumping, and the characterization of alternative materials and treatments. And in any case, I have to say that a possible collaboration between CERN and the Einstein telescope in vacuum technology is perfectly in line with the recent update of the European strategy for particle physics, which call for a strengthening of synergies in areas of common interest and mutual benefit. Thank you very much for your attention.
Thanks, Paolo. There are a few questions. Fulvio.
Thanks, Paolo. It's a great talk, very impressive. The question concerns the couple of last slides that you have shown concerning the mild steel. You pointed out that this is the test done on samples as has been received. What does it mean? These were just received from a company without any treatment, for example, treatment of the surface. And have you measured before to do the test the roughness of this of the two samples, 304L and mild steel, and which kind of company provided you the mild steel? That's all.
Thank you very much. So the as received means that we place an order in, I think it was in Switzerland. Is a reseller of steels. I think is to my knowledge is a Japanese steel. Sorry, is a Chinese steel. And we are measuring now the roughness. Sorry, I can give you that next week. Okay, and the only treatment that differ from the two samples is that the mild steel was cleaned by solvents, in particular modified alcohol solvents, while the 304 was cleaned by a standard process used at CERN for this material, which is based on aqueous environment and detergent. We used the solvents for the mild steel because of the risk of induced additional oxidation of the surface.
Yeah.
And the formation of hydroxide, which is maybe a problem for water desorption.
Thank you, Paolo.
Agnello?
Yeah, very interesting. This outgassing of low carbon. But the point is the corrosion in carbon steel. And do you have plan to also to study this aspect that is very important for facility like FSC or AT that should last 50 years in operation at least, and even if in a good environment, but still corrosion is an issue. So.
Yeah, I fully agree with you. This is one of the most important and serious problems for this material. And this is the reason why it's not used for vacuum systems in general. As Joe already pointed out at the beginning of this day, there is a enamel treatment of the surface, external surface, or other anti-corrosion treatments. I know that the your American colleagues are quite skeptical in using tight coatings on the external surface, because in this way there would be no chance to detect any leak developing, for example, on the longitudinal welding or close to the flanges. But certainly this is one of the most serious and important subjects that we have to address in the next years.
Yeah, thank you.
Okay, thanks again. And of course, we will follow this up because this is really very important for ET, and so we will know how to find you. So thanks again.
Thank you.
We also found Takashi. And Takashi, can you finish your presentation?
Yes.
I think you came to slide 14 and then it stopped.
Yeah. I am very sorry for my lost connection.
No, that is not.
Now I'd like to share my screen.
Okay.
Can you see my slide?
Yes.
Okay. Let me start from this slide. So I'd like to talk about temperature and humidity controls. So keeping temperature stable is important because temperature change may affect our low frequency vibration isolation systems. And humidity control is also important to keep instruments healthy. So in the laser rooms, temperature must be most stable. And heat generation is quite different between commissioning time and observation time because of the number of operation of fan filter unit that generate clean air inside of each station is different. So to keep humidity in the experiment room, we injected dry air from outside. And for the temperature control in the laser rooms, we equipped two precision air conditioners. And to control temperature in the corner station, we introduced four coolers to compensate the heat from 250 fan filter units. So to control the temperature, we have to make a good balance heat sources such as fan filter units, vacuum pumps, PCs, and so on with coolers. This is the current situation of Kagura. Here shows the temperature changes in Kagura and at outside. These plots show the temperatures in the experiment rooms, and it looks well controlled from this time. And this line, this plot shows the temperature at outside, and it seems not to affect temperature in the Kagura experiment room. So this is one of the merit of underground site. Here shows the humidity changes in Kagura and at outside. These plots show the humidity in the experiment rooms, and all of them were kept less than 70%, thanks to the dryer injection from the outside. This is our final topics, water issues. So this graph shows the amount of drain water in wire. So as I talked, Kamioka is the area. Kamioka is the area with heavy snow. So that as a result, amount of water increases after the winter season, like this, and like this. So that we have to fight with a large amount of water in the site. This slide shows spring water treatment from walls in the corner and end station. Here is a surface of rocks, and it's covered by spread concrete, in addition to covered by bubbling uretane. In addition, covered by anti-water plastic paintings. And in addition to these things, we covered by walls by vinyl sheets. This shows our vinyl sheets, and here, this shows anti-water plastic paintings on uretane. But we could not stop water leak from anchor point, such as here. So these are terrible things. This slide shows spring water treatment from walls in arm tunnel area. We just put a vinyl sheet like this. But not for all area, and some several places are still water droppings. It may make noise. And this slide shows a floor spring water treatment in each stations. So this figure shows a current Kagura floors, and this figure shows the ideal floor design. So we completely missed to estimate the amount of spring water from the floor levels. So we should make enough layers of concrete floor to reject water flooding from the floor. In addition to this, we should make deeper ditches. Those are the necessary. At present, we made several deeper holes like this to collect waters and put small water pumps to transfer outside the station. But these pumps may be the noise in the future. But we can do anything else. This slide shows Wayam tunnel spring water treatment. So water in the YM is a lot because of known faults. From the end of snow seasons, our YM central part, from 1 kilometer from the center area to the end of YM tunnels was covered with water like this. To avoid flooding, Kagura has a drain relays using water pipes, such as this, like this, and outside. And also, we constructed vertical drain hole at here to drain the water in the wire. This slide shows the exam tunnel spring water treatment. So in the case of exam, we put a larger drain pipe under the floor. Then we could avoid flooding so far. But the water from this exam is transferred to the drain pipe in the adults access tunnel, our main access tunnel to the Kagura site. But because the drain pipe is insufficient below floors in the access tunnels, so there is a flooding in the access tunnels like this. So what we learn from this is it is important to design how to drain water systematically. And this is our final slide. And Kagura is constructed in the Kamikaze mine. So small seismic motion is available inside 50 meters or more. Microseismic motion caused by intense ocean waves is terrible. So we have to balance heat sources with cooler to make temperature stable. Dry air injection from outside is needed to keep humidity under 70%. So systematic and careful design of water drain is important. That's all. Thank you very much.
Okay, thank you. Are there any questions? Let me look in the chat window.
Can I ask one question, you?
Yes.
Thanks for your wonderful talk, Takashi, furiously speaking. Can you tell us few words concerning the safety issues that you faced during the construction and now to manage the access to the tunnels? Safety.
What? Safety during excavation or current?
Yeah, during the excavation and the present situation. What are the facilities for the safety?
During excavation period, safety management has been done by company itself. So that we didn't special things for safety.
And now the safety.
Now, so to maintain tunnels, so we every 2 weeks, we investigated all the tunnels by specialized people in the mining company, and we found we found many things from this investigation. So I should show. Okay, this slide shows recent troubles in tunnel structure. So we found how hand-sized concrete pieces fell from the arm tunnel ceiling. So like from here, they like this weight of this of 500 grams. And another, so if these things hit on the vacuum tube or vacuum barrels, it might be terrible. So that we protected barrels like this, or like this metal covers. And another troubles in tunnel structure is we found cracks on the tunnel walls, several positions in our tunnels. For example, X-arms or access tunnels or bypass tunnels. So like this. And we have already addressed these problems by mining company. And so cracks. So we have already repaired walls. And okay, those are the troubles in tunnel structure recently happened.
Yeah, but there is also the issue that the end station and the X arm, that there is no escape there. So you have a kind of a
yes.
room in that area.
So this is a Kagura tunnels, and corner area has a two entrance. So here is this is a one entrance, and here is another entrance. So if we encounter accidents, we can escape from here or here. But if accident happened in X end is one way, just one way. So that if accident happened in the X arm, people working in X end should stay in X end. So that we prepared emergency shelter in X end.
There was a question from Peter.
Yes, thank you. Actually, I would like to ask the question of Didier Ferkin up in the chat. So what is the reason of the higher seismic noise at the deeper station? I think a deeper corridor. I think it was the slide 12.
Slide 12?
No, 12.
12.
Yes, here. No,
this.
Yeah,
yes. This one.
No, this one. Yes. The red line. No. The next one probably. The red line goes above the green at about 30 hertz and above. So what is the reason?
I'm not sure the reason, but
No, maybe we can take this one then offline.
Maybe sound or sound condition may be different at the measurement point, but I'm not sure what happened at the 800 meter.
Okay. Thank you.
Good. There was in the chat window some discussion about Newtonian noise from the water flowing. And I think people believe that this is probably not an issue.
Yeah, we also think water drain may be the source of Newtonian noise. So that I included this talk, but we are preparing water monitoring of amount of water go through the Y-end station.
Good. I think we stop here. So let's thank all the speakers for the beautiful talks this morning. And we are convening again at 2:30 this afternoon. Okay, so thank you very much and see you